because this is really interesting, and this coefficient thing, it's such a smart idea, and it would be lovely if something came of it, even if you just did a program and something seemed to happen. Yeah. It would be very interesting to know. Even if you end up saying, well, we think these 6 coefficients are good, but we can't prove anything, that's fairly pretty interesting.
For next year.
For next year, yeah, I'll tell you, yeah, so I'll give you a new problem now, but do keep thinking about this one, do keep thinking of thoughts about this.
Yeah.
All right.
I'll definitely come back with a solution.
You should. I think that's honestly. Sig bare, det er et godt argument. Altså, det var lækkert. Altså, det kom sådan lidt ud af det blå. Jeg har ikke haft noget ved det at gøre.
Ja. Jeg har vist lidt mere det der game theory.
Jamen, det er godt. Det må du godt tænke lidt videre på.
So I'll draw some pictures and I'll give you a sequence of problems which end up with the real problem.
Okay.
Okay. So it's nice of games this time.
Okay.
It's just about a sequence of numbers.
Mm-hmm.
Okay, so I'll write some numbers on the board. They're numbers. They're positive whole numbers. So you can't say -4. There's no 2.5. Just some numbers, and they go on. Let's say forever.
Sure.
Okay, so 2, 1, 15, 13, 6, 9. Just like that. You can't have a repeat, by the way. They've got to be all different.
Okay.
So if any 2 numbers, one of them is bigger, you can never say, oh, they were equal.
Okay.
Make sense?
Yeah.
Okay. So maybe I'll just stop at length 6 for a moment. So here's a sequence of 6 numbers. Okay. Now, inside that sequence of 6, I guess I can see, I don't know, let me just add something on here. I can see 3 places where the numbers get bigger. Like if I went from, say, this one to that one to that one, the numbers are getting bigger, 1, 6, 19.
Mm-hmm.
Is that right? And if you named, I could say this was the 2nd term, the 5th term, the 7th term. Right, so in this example, I went from the 2nd to the 5th to the 7th, you're going up all the time.
Mm-hmm.
Okay. But I don't really like that because those aren't equally spaced, 2nd, 5th, 7th. So if you look more closely, I guess you could see, I guess these are also increasing, and that's the 1st, the 4th, and the 7th, right? 1st, 4th, 7th. And 1, 4, 7 are equally spaced.
Mm-hmm.
Do you have this word arithmetic progression?
Probably
AP?
not in.
Okay, just 3. I'll say equally spaced. 3 equally spaced. Okay. Actually, even this one is 3 equally spaced. Make sense?
Hmm?
Because I don't care about the space between the numbers. I only care this is 3 more, 10 more. I never care what the numbers are. It's only about bigger or less than. Okay, so if I took the same sequence and replaced 2 by a 3, it's all the same properties.
Hmm.
It makes sense? But what I'm saying is, maybe you can, maybe you can't find, let's say, 3 things which are going up and they're equally spaced, or going down equally spaced.
Mm-hmm.
Maybe you can, maybe you can't. Right? If as a silly example, if I give you this sequence, 2, 1, 4, 3, in that one, you can't even find 3 places where it goes up, right?
Mm.
I can't find you a number, then a bigger, then a bigger. Okay. And so I certainly can't find 3 equally spaced that get bigger. And also, if you look, I can't find 3 that get smaller. Okay, this example. Right, so that's what we're doing. We'll be looking at a sequence of numbers. I never care what the numbers are, right? Only care with the relative, which are bigger than which. And I'll be asking questions like, can you find 3 equally spaced where you're either going up or going down?
Mm-hmm.
Makes sense? Or maybe 4 equally spaced, something like that. Okay, so here are your tasks. Okay, so the first 2 tasks, it's kind of fun exercises. I don't know which one's harder. I don't know which. I just mentioned them both.
Mm.
The first one is if you have an infinite sequence. So if it goes on forever, then you must always have 3 equally spaced places where you go up. You must always have 3 equally spaced and actually go up.
Mm-hmm.
However, weirdly, if I said to you, okay, that's fine, is that true for length 100? The answer is no. So the answer is, if I tell you I want 100 numbers, please, you can find me, it's a nice exercise number 2, a sequence of 100 numbers so that you can't find me 3 equally spaced that go up or that go down.
Mm.
So this, I'll say, for every number n, find a sequence of n terms with no 3 equally spaced going up and no 3 equally spaced going down. Does it make sense?
Yes.
Right. You might guess these examples that actually, once you're at length about 7, you always do find a 3 up or a 3 down, but actually you don't.
Mm.
Okay, and even 700 you don't. It's quite a weird contrast here, right? So for any number n, you can find a sequence that works, so length n, but you can't find an infinite sequence that works. A little bit weird. That's not impossible, by the way. So here are 2 very stupid statements. Ready? Do you agree with the following statement? If I want you to find me a sequence of 100 whole numbers, 100, where each one's less than the previous one, you can do it.
Mm.
You agree? 100, 98, down to 1.
Mm-hmm.
If I said, okay, I want, actually no, I want 1,000,000 numbers. Each one is less than the previous. You can do that as well.
Yes.
If I said I want an infinite sequence,
Hmm.
each one through, then you can't do that, can you?
No.
If you're restricting to positive whole numbers, right? There's no infinite sequence of decreases, because if you start with 1,000,000, then the entire million you hit 0 and you die. If you start with 1,000,000,000, you hit in entire billion, you die. Does that kind of make sense?
Yeah.
So what I'm saying is, these two could, but they are both true. I promise you, they're exercises, but they're not. It's not. You can't just say, wait, those can't both be true because if it's true for every n, it's true at infinity. Which is, right? If you ever think, how can this both be happening? Think of the example of decreasing sequence. Okay. So again, the first part of the thing is to say that for any n, you can have a sequence of n numbers which don't have a 3 up or 3 down. Right? 3 up, I mean 3 equally spaced going up. Okay. And yet, with an infinite sequence, you always do have a 3 up. Okay, so that's the first thing. Yeah.
Can't you just have the same number in the
You
sequence of n?
never equal. All numbers have to be different.
Right.
Okay, so
That makes
you're
sense.
never allowed to repeat. So any numbers are either going up or go down.
Mm.
You can't cheat with equality. Okay, that's one question.
Okay.
That's the first thing. Okay. Then the next question is to find an infinite sequence with no 6 that's up or down. So again, I promised you, and you'll prove in this exercise, that when you have an infinite sequence of numbers, you can find. So there's an infinite sequence that you don't find 6 in a row going up or going down.
Mm-hmm.
And then question 4 is the same with the 5. And the real question is, what about with the 4?
Huh.
But I don't know the answer to that one.
Okay.
Okay, so here's the official final project. It is it true that in an infinite sequence, again, of whole numbers and positive integers, infinite sequence, can you always find 4 equally spaced ones where you either step up or step down? Does that make sense?
Yes.
Okay.
How odd that that is unsolved.
It's weird, totally perfect reaction. How can that possibly be unsolved? It's good. But so if you think about it, I would first convince yourself that For 3, there's no bad sequence. You can't find an infinite sequence for 3 that doesn't have a 3 up or 3 down. You always can find a 3 up, 3 down.
Okay.
Then you should find me a bad sequence for 6, then a bad for 5, and then maybe find a bad for 4 if you can, but anything else that one. And the kind of word of warning is that these are always about infinite sequences. You can't ask these questions of finite setting, because in the finite
Right,
setting,
of course.
i.e. length n, you can already find a finite sequence of length 1000, which doesn't even have a 3 spaced up or 3 spaced down. Okay, yes?
So you can't use the same number again
Yeah,
twice.
that's right.
That's
So
important.
so you can use 1 and in the million terms 1 again.
Nope.
Can't you do that?
To use one once. Yeah. But again, note again what the actual numbers are doesn't matter, in the relative order matters.
Yes.
Right? So whenever I told you about this sequence, if I multiply each by 10, it's the same sequence.
Yeah.
Right? All that matters is the relative order. And I want always and a 3 or 6 always means equally spaced. That's kind of important.
Yes, of course. Otherwise, it's quite easy
So,
to
yeah.
solve.
But I say before you think about the actual problem, I would definitely warm up by trying
Yeah, yeah.
these 2 exercises, and then I think you should do this and this,
Yeah.
and then go on to this.
Exciting.
And I don't want to say how you should think about infinite sequence.
No, please
I
don't.
I don't
No,
want to
don't.
perturb you. I want you to have your own ideas.
Yes, perfect. That's perfect.